Hey guys, it's Andre here, and today we're going to be doing another competitive programming video for the Learning to Program with Andre series. I think you guys will enjoy this problem. It's an easy problem, but it's got a unique solution. It's like mathematical solution. It took me a little bit initially to think about the best solution, but yeah, it was pretty fun. It's rated 1,000 points on the hacker rank difficulty, so it's pretty easy. But let's get to it. Okay, so I have divided the problem into the text, the input, and the output, and the solution. And that's all gonna be on my GitHub, and I'll put the link on the description of the video so you can download it. The link to HackerRank as well, so that you can look at the problem there, submit your own solution if you want. I'm gonna print the problem real quick. I'll explain it very briefly. There's gonna be a link to this again, so you can just download it and read it carefully. For now, I'm just gonna explain it quickly. So basically, Riley is a bad boy, and he's got some yo-yos. Your friend Anton lives in a room, and the room can be defined as a n by m matrix. He's gonna have a start position, and Riley can place two yo-yos in any two cells. It can be the same cell or different cells, and Anton will take the shortest path to pick up both of the yo-yos and to go back to his original position. And you have to maximize the distance that Anton covers. So I'll show you a very brief example. So let's say we have a room. Oh, this is a room. It's a 1, 2, 3 by 1, 2, 3. So this is a room, right? It's a matrix. And let's say Anton starts here. Well, we could put maybe, and I'll do it in green. We could, no, maybe like blue so you can see. We could put like a yo-yo here, and then one here, and then Anton would pick them up. So he would take 1, 2, 3, and 4 movements, right? Or we can do better. For instance, we could put a yo-yo here and here, and he would take 1, 2, 3, 4, 5, 6 movements, right? Okay, so let's look at some of the input and output solutions. Okay, so the first problem, they're saying that the room is of size 2 by 3. So we'll make the room real quick. So 1, 2, 1, 2, 3. And if Anton starts at 1, 1, the optimal solutions for the yo-yos is 1, 2, and 2, 3. So if he starts at 1, 1, the yo-yo 1, 2, and 2, 3. So it would take him 1, 2, 3, 4, 5, 6. 6 moves. Can you find a better position? Note that there might be several answers that give you the same amount of moves, and they're all correct. For instance, we could have done 1, 2, and 1, 3, and this would be the same. It would be 1, 2, 3, 4, 5, 6. As a matter of fact, any combination like this would provide, except for this one, any combination that goes through that path would provide the optimal solution. Let's look at the next example. This one might be a little better. The room is of size 4, 4, and he starts at 1, 2. So let's make a 4 by 4. Okay. Okay. 1, 2, 3, 4. 1, 2, 3, 4. And Anton starts at 1, 2. 1, 2. And it's saying the optimal solution is 4, 1 and 4, 4. 4, 1 and 4, 4. So he has to go through this. I'll just draw out the line. Basically, the outside, the perimeter outside, right? So if possible, you want to pick stuff on the outside corners, right? But what if he... What if Anton is here? Do you think this would still be the optimal solution? It probably wouldn't, right? It would be better to do this, for instance, or maybe... I guess you wouldn't, yeah. It would be definitely be better to do maybe like this, right? Maybe even this. Boom, right? So it's not always picking the bottom corners. So now that you have seen a few examples, and I'll have a link to this so you can look at the base samples on your own. I want you to pause the video here and think about how you would solve this. Think of a solution. After this, the video is going to resume and I'm going to explain my solution and how I solved it. And but yeah, I want you to pause the video here, think of a solution, and put down your solution in the comments. Okay? So this is my solution. What I ended up doing is actually calculating the Manhattan distance in between the input point I and J and the two top corners, so the top left and top right corners. And the Manhattan distance is given the points described by the coordinates x1, y1, and x2, y2. You can find the linear distance in between the 2 points by doing the absolute value of x1 minus x2 plus the absolute value of y1 minus y2. And based on that, I found which corner was farthest away, and then I simply either picked the top left and bottom right corner or the top right and bottom left corner. And that would force you to essentially traverse the entire grid, maximizing the amount of squares that you had to travel through, which was what the problem required. It was a very unique mathematical solution, but I like this problem because of that. I hope you guys enjoyed.